Welcome to this course on understanding neural networks. This is the first video of the course and it covers one-to-one gradient descent. Gradient descent being the backbone of machine learning, of deep learning at least. So this video is going to introduce gradient descent in a very simple way so that we can build on that and later on get more complex networks to work. So first we have to get used to some new vocabulary. We have to weight being denoted by a W, which determines to what extent a particular variable is important. So that variable might be an input, might also not be an input, as you will see in later videos. It could also be a hidden node in a hidden layer of the neural network. But for now, it's just going to be an input. And then we also have the input, which is then in test time used to make predictions. So for example, we have this cute cat here. So if you would go to any human and ask them, what is this? They would say, well, that's a cat. But if you go to a computer and say, is that a cat? Well, like, how should I know, right? So how it's going to learn is that it's going to have weights. They're going to tell the network to what extent a particular pixel, because the input is going to be, in this case, just a lot of pixels. To what extent a pixel is important. So and then the hypothesis function is the mathematical definition of the neural network, aka the output for a given weight W and input X. So if you have an input, so for example this image being X, and then you have some W that you've learned, then the hypothesis function is the one that predicts whether or not this is a cat. And then there's also the target, which is only used during training. So there's training and test time. During training, we're trying to change W to make all the input to have a better fit for the input and the target. So we're going to have, during training, we're going to have a lot of data pairs being X and Y. So that's just one data pair. So we have this, our X, and Y being 1 because it's a cat, and 0 for non-cat, but this is a cat. And so that's going to be the target. So for this one, X is the image and Y is 1 for being a cat. Y is the target, which we only have during training. Now loss is the loss function, also only used during training, and it determines how far off the prediction is from the target Y. And so if the algorithm were to say, well, this looks to me like a cat, then the loss function, the loss would be very low. It would be 0.01 or something like that. I don't know, but it would be very low. But if the algorithm were to say this is not a cat, it would be quite high. And it's not going to be. It has to be a continuous function, so no jumps in between. And it is a non-negative function. There cannot be a negative loss because we're trying to minimize it here. Gradient descent is a method which mathematically minimizes the loss function by changing W for some data pair of input and target X, Y. So if the loss function would have negative outputs, if it might have negative numbers, that will completely throw everything off, and it just is not. So yeah, so gradient descent is a mathematical way to minimize a function, in this case a loss function. And minimizing the loss function as it's showing how far off we are with the prediction to target basically means that we get a better approximation. So using gradient descent, by minimizing the loss, we have a better weight, which will have a better hypothesis function, which will be used during test time, or rather application time, or whatever you want to call it. Wow, I made animation for this and now I don't even use them. Great. So definition of the hypothesis function. So this is two ways to represent the hypothesis function. This one you often find in textbooks. It's a more visual way. So this is a node. Every node is a value. So right here we have a node with X. So that's just one value. The input X. So for example, if we were to say want to map an age to a height, then this might be, well, 2 years old, and then the prediction is going to be, for this network, is going to be x times y. It's going to be the node times the connection. So this connection has a value of y. So this is just a visualization. Don't get too confused with this. This is the same thing. So now we have the hypothesis function for this simple network defined as x times w. Now we want to define the loss function. So the loss function should be greater if we are further off the target, and if we're close to the target, it should be very small. So this one, there are multiple different ones for different applications, but this one is called the mean squared error. It's a simple go-to basic loss function, and the mean squared error does exactly what it says. It takes the mean square error. So we have the error here being the difference between the prediction and the target, so prediction minus target. So if we say yeah, this 2-year-old child must be like 10 meters tall, right? And it says no, actually not, it's more like 1 meter. And it says like, damn it. Then we have a 9 here, and that's going to be a loss of 81. This squared term has two important uses, I guess. For once, it makes it so that this is always positive, right? That was an important thing I mentioned earlier. It has to be positive. It also makes it so that so if you change the prediction when we are further off the optimum seems to be 2. Yes, here the target is 2. If we're further off the optimum, a change in the weight has a way bigger impact than it had before. So I mean, than it had down here. For example, if we were to take a step down here, this much, we would get down like 0.5. But if you take the same step here, we would get down like I have to be accurate though. 1 or like 1.5, something like that. So this is a big advantage that this loss function has the mean squared error. I would advise you to write that down as well. So now we have the loss function here defined as function of y, x, and w being defined as the prediction of w and x minus the target, and that's squared. Right, so this is going to be an example. So for example, if we were to have an x equals 2 and y equals 1, so some child is 2 years old and 1 meter tall, and that's quite tall, but whatever. We only the algorithm. So now we want to change a w that has the best fit for this data pair. So we would say, well, the prediction is, let me see, x times w equals y. That's pretty easy. We divide by x, and we have w equals y divided by x. That is true. I cannot deny that, but it's not useful later on. For now, it works, but later on, I think when we get to deep neural networks, that's before that you can still do it, but when we get to deep neural networks, this is not possible anymore. So we have to already think the other way to then later on not get stuck. So I want to do a thought experiment with you here. So we have the loss for x for what it means that they are not in the bracket means that they are fixed numbers. And it's w that we're looking at. So we have the loss function for some given xy in respect to w. So that's what we have here. And that is equal to, as often defined, the hypothesis for some given x in respect to w minus y squared. So now when we replace the prediction by this term, we get this. And if we look now at the loss in respect to w, we can see that it makes a lot of sense, right? So at 0.5, which was the optimum, the loss is 0, and at the further we get away from this optimum, the higher up we go in the whatever you want to call this, the mean squared error function. So now the definition of gradient descent. So gradient descent is an algorithm that mathematically changes w to minimize loss. So loss already defined before. And what it uses is the math principle of derivative as a sum function f of x. Then the derivative, this term here, and if you never heard derivative before, don't worry, I have a link to a really good explanation in the next slide, or like the one after the next slide. But stick with me here, this is still important. So if you look here, for some f of x plus dx being a small change we make. So if you look here, dx is 0.5, so we change it by 0.5. That's not a small change, but it's just for visualization's sake. Then what we want to know, what is the change we get in the loss function when we change the weight. So this basically translates to, if you change the x, so this should be the w. So if you change w by a really small amount, we're going to have f on x, which is this one. So this, so if you have, so right now being x equals to -1 in this example here, and dx equals to 0.5. So f of x plus dx is f of -5, because it's -1 plus 0.5, and that seems to be a 4. That's exactly 4. So now we say 4 equals to f on x, being x of minus, which is still the -1, which is 9, plus that small change we made, which is in this example not small, but 0.5, times the derivative of the function. Derivative basically just means slope. So the slope at this, so how steep is it at this point? So we go to, and that's the definition of the derivative. And this only works for dx that is that is so tiny that it's not even defined as a number anymore. It's actually just say dx approaches 0. But if you look at this now, so this you could hypothetically say that this this slope, you could define it with these 2 points. Then you say difference in y divided by difference in x. Difference in y is -5. Difference in x 0.5. That equals to -10. And if you plug this in here, this works. But this is kind of cheated, because this is not the derivative. Derivative means that you don't take the slope given 2 points, but you take it just given 1 point. And that is a mathematical concept that is used here. And again, if you didn't understand this yet, that's totally fine. I'm going to link a video and the next slide. So let's apply this to the loss function. So if we change w, down there's the loss. If you change w by a small dw, we actually only want to know the change. We do not care. We do not care about the first part here, about the loss for given xy in respect to w. We don't care about that. We care about the second part. So if we change w now, how will that affect the loss? And we also we obviously want to have it affected negatively. So what you could do now is say, well, if the derivative is positive, that change should be negative, because that last term here, the dw times the derivative of the loss, should be negative, because you want to decrease the loss function. That's why we could say, hypothetically, that if the loss is positive, the derivative of the loss is positive, then we would have a dy be a negative number, and if this is if it's negative, then we would have dw being a positive number, and that would totally work. So if you would plug this in, this will probably jump like this, and then we'll go over this, and then we'll hop between these 2 points all the time, because it always has the step size of exactly 1, or exactly whatever you told it to. This will not converge properly to the optimum. That's why we do something else instead. We make the change equal to the negative of the derivative itself times some alpha. I'm going to get the alpha later. Alpha. So you take the negative of the derivative. So for example here, this is a very this is a very so right here. If you look at the slope right here, the derivative is quite um, big because the slope at this point is quite large because we're going quite steep already, and it's a positive number because when we go to the right it increases. That's a big positive number. So if you look here, a big positive number, so we do a big negative step, so that would put us right there, and then would already have a very small loss. So that works perfectly well. So that's exactly what we want. So we want to make bigger steps the steeper it is, because right here, if you would do the same size, if you do the same step again, there's quite a big step, then we would end up here and then here again. But now the slope is way smaller. So now we're going to land here, and so on until we converge to this global minimum. This will work, but it might just make too small changes or too big changes, mostly too big changes actually. But so if you were just to apply it without the alpha, it would be right here, and it would say that's quite a steep slope. I'm going to go right up here, and that's a problem because from here it will probably go up there, and it will just continue bouncing around and um, going to orbit, which we don't want. We want quite the opposite, so that's why I put an alpha there, so we make it smaller, so that um, it's not actually too big, so that we just jump over the global minimum and just keep bouncing. That's why we have that alpha. Um, so now we have the derivative of the loss function. Um, so this is important. If the following step doesn't make sense to you, watch the video on the next slide, or the video series rather. So obviously you have to find the hypothesis function as of wx being equal to x times w. Now the derivative of the loss for a given x and x and y in respect to w is equal to, this is the mean squared error, and then the derivative of that. So we replace the prediction here with what it says here, and now we take the derivative of x times y minus y squared, which turns out to be exactly this. You can check that yourself. This is what it turns out to be. So the 2 hops on front, then the exponent gets subtracted, and we subtract the exponent by 1, so it's 1, so we can leave it. And then because of the product rule, the x hops out. So if this doesn't make sense to you, it's fine. Online learning helps you now. So on the right here, there's a link to a series that 3 Blue 1 Brown did, and that's on derivatives, and it's really good. So you would probably have to watch the first 4 episodes, and then you can come back here. And I think the first 4 episodes will have you covered for the next, for the next 5 math episodes probably. Maybe after this you want to continue watching it, but it's also very fun. So it's just a win-win situation, right? So now, so either you're back, or you're already you are already able to do calculus before for some reason. So now we have the gradient descent applied. So this is the pseudocode which we're going to work with. So we have w equal to some random number. Again, that could also be 0, but just get used to using random numbers at the start. It really helps the algorithm, but whatever. Now we repeat for training steps. In this case I did 10, and we have the change equal to the negative derivative. This is the derivative times alpha. And I set alpha to be 0.05 or something like that. At first I had it at 0.5 and then just bounced around, and it went to orbit exactly what it shouldn't do. So I now had it at 0.05. So now if you see here, this is the input, this is the data pair we want to get right. So this is the hypothesis function for a given x in respect to x. So you can see right now, this is the function w times x, right? So this goes downwards because w right now is -3. So if x increases by 1, the hypothesis function goes down by 3 because the change is obviously -3. Then we have the loss function here. we're right now at this point. The weight is equal to -3 and our loss is equal to 100 and something, 190 or so. And this is loss over training now step numbers. Now if we do one step, so this was one step. So the function is already a better approximation. Note that it always goes through 0. This is a problem we will fix in the next episode, but basically this is happening because if x equals 0, well, since the function is w times x, if one of the factors is 0, then the product is 0. That's just how it works. So we already have a better approximation of this point. And as you can see, we changed w, and we therefore went down to have a way smaller loss, being only like 50 or something. And we can already see that this made a huge difference in our loss right here over the training step number. So this is the next episode. We got better still. We are converging to our global minimum. You can see that this step it took here was way smaller than the one it took before. So this one is a way bigger step, and this one is a way smaller step. That's just why, because the slope here is way steeper than it is here. So now we're going to have another one. See, this is already looks kind of flat already, and another one. Oh, look at that production quality! I centered all of them in the same center. Not. Now this is, while this is converging to this dot, you can see that it's converging slower and slower. So when before it made a huge gap, and now only makes very small changes, just because you can see here the slope at this point, right? It's super small already, and you can see this exponential, I guess counter exponential graph. Looks like a anti-proportional function. But then if you go through I think this is the last training step. Yeah, this one is it. So this is the 10 training steps I've trained it. And it looks really good. It figured out how to approximate to this one data point. And yeah, that worked pretty well. Obviously this has still a lot of flaws. For example, it has to always go through this 0, and it can't just be anywhere on the y-axis. It always intersects at x at y equals 0. And then also there's only one data pair now. But that doesn't help at all, because a lot of functions fit this one data pair. So if you have this function fits it, this one fits it, this one fits it, they all fit it. So we want multiple data pairs to actually have a reasonable and good algorithm. So that's what's going to happen in the next math video, being multiple data pairs and bias. And the coding exercise is going to be the next video I'm going to put out in a few days, and that's going to be using Python to implement what we just did. Last but not least, join my Discord. You can ask questions, give me feedback, comments, concerns, anything you want. So join my Discord, link is in the description. So go to my Discord and then watch the next video if it's out yet. If not, you're quite eager to watch my videos, and that's weird. But yeah, see you next time.